Okay, welcome back to Easy Concept. So today we are going to start the steel structure short note. Okay, plastic analysis. Okay, that is a chapter number 1, plastic analysis. Plastic, plastic analysis of structures. So that is a chapter. Okay, here we are going to see about the introduction about the analysis, and second one is assumptions, and assumptions on plastic analysis. Plastic analysis, and the third one is this is the assumption, and the third one is determination of shape factor, and the fourth one is collapse load calculation, and the fifth one is length of plastic hinge. Length of plastic hinge. So I have segregated this chapter into 5. One is the introduction, next assumptions on plastic analysis, next is the shape factor, next the collapse load calculation, now the length of the plastic hinge. That is the last part. See, first of all, in the introduction part, in the introduction part, we are going to see the stress strain curve. The stress strain curve for mild steel, which was something like that. So this is the stress, and this is the strain, and this is the strain. Okay, and the stress strain curve is something like that for a mild steel. Okay, now up to here, this point is the elastic point. This point is the upper yield point. Somewhere here is a proportional point. This is O. This point is A. This point is B. This point is C. This is C dash. This is D. And this point is E. And this point is F. Okay. These are the some of the important points. Okay. Important points. Now this point A, we can call it as proportional limit. Point A, we can call it as proportional limit. And the point B, which we are call it as elastic limit. Point C, we are call it as upper yield point. C dash is, we can call it as lower yield point. And C dash D, we can call it as yield plateau. And capital E is ultimate point. And F, we can say, is a breaking point. Breaking point. Okay. See, in the analysis, generally for working stress method of analysis or the RCC, working stress method, we generally consider the steel within the elastic limit. That means we will curtail only this portion diagram we have taken for our analysis. Okay, only this. So if you draw the stress strain curve after idealizing, this is the idealization, we have considered only this part. The remaining part we didn't consider. So this is the stress, this is the strain. Okay, this is the idealization of stress versus strain, stress versus strain curve. Okay, now what we can do for steel. Okay, for steel, how it will be. For steel, okay, whether it is a, yeah, generally it's a plastic analysis, we will idealize this into up to the yield plateau. We will idealize this entire thing for our analysis. Okay, this entire thing we will idealize, and in that we will ignore this portion. We will ignore this portion so that the idealization will be happen this and this. Okay, so for a steel structure the idealization will be something like that. We will idealize something like that. This up to this elastic, up to elastic, then we will not consider the upper yield point and lower yield point. We are just curtail this, take out, and we have to idealize from this elastic point to the yield plateau. So this is the idealization for steel structure. Okay, and the stress corresponding to this point we can say is yield stress. Okay, now this is the strain. Okay, and this strain. Okay, this strain we can call this is the elastic strain. So up to here this strain is elastic strain ey. Okay, now the remaining strain, this strain, the plastic strain, should not be less than 6 times the ey. This strain you have to consider, this strain, plastic strain, should not be less than 6 into ey. So this is the idealization. Okay, first actual stress strain curve is something like that, but for our analysis we are considering up to the yield point, and we taken that so not yield point, yield plateau, and we have taken that point is equal to 6 times the e into y. Okay, where ey means what? Elastic strain. Vey is elastic strain. Okay, so that's first is over. Now we are going to the second part, that is assumptions on plastic analysis. Assumptions on plastic analysis that we are going to see. First one, assumption number one, that is, let us take A. Plane section remains plane before and after loading. Remains plane before and after loading. This assumption is called Bernoulli Bernoulli's assumption. This assumption is called Bernoulli's assumption. That's the first assumption. Okay. It says what? This assumption, plain section remains plain before and after loading, means we can say it implies that only strain varies linearly over the depth of beam, linearly over the depth of beam, meaning, so initial shape of beam is this is the initial beam. Okay, then after bending the beam comes something like that. After bending the beam comes something like that. Okay, this is the beam. Now, so this is the strain diagram. This is the strain. This is the theta. Okay, so we can say this is the strain. Now see, this strain is a linear. So this is the linear strain. Okay, and we can take it as this is the neutral axis. This is the neutral axis. Okay, now bending strain is equal to E. We can write this is a delta L, this opposite side. Okay, that is a maximum strain, opposite side. So for delta L divided by L. So this is the total strain. This strain is equal to delta L by the total length of the span. Okay, so that's the thing. Now here one point we have to keep in our mind, that is, note this assumption, this assumption only valid only valid up to collapse load, up to collapse load, or we can say failure load, up to collapse load or failure load. So this assumption is only valid up to the collapse load or failure load, not more than that. Okay, now we can move for the next assumption. Assumption number B. Okay, here the cross section, here the cross section must be symmetrical with respect to the plane of loading. Okay, means if the cross section is not symmetrical, if the cross section is not symmetrical with respect to the plane of loading, then twisting moment are developed, twisting moments are developed in the beam, and fluctual formula cannot applied directly, then the fluctual formula cannot apply directly. Okay, meaning If your section is, for example, a T section, for a T section, this is the plane of symmetry. So here the cross section is with respect to symmetrical about the plane of loading. So this is the symmetrical about y-axis. Okay. So if you give a load, then it is the load centroid will coincide with the centroid of the section. For example, a rectangular section also symmetrical about y-axis, symmetrical about y-axis. So this also UDL, but this load is now coincides with the centroid of the section. But there was a I section, sorry, L section. The L section is not here. The load is somewhere here. This is the load. You know, the centroid of the load and the centroid of the section is not coincides to each other. The centroid of the load is somewhere here. Okay, so this is the eccentricity. So this eccentricity produce some twisting moment. Okay, so that's a point. If the cross section is not symmetrical with respect to plane of loading, so for L section, is L section is not symmetrical about the plane of loading. So this is the reason there was a twisting moment will be developed in the beam, and the fluxual formula cannot be applied directly. Okay, so for these two cases fine, but this case is subjected to twisting moment, so the fluxual formula we couldn't able to use. Okay, now next assumption, C, the beam subjected to pure bending moment. Pure bending moment. Okay. Now pure bending moment. That's a next point. Next one is D point. The effect of, okay, what is the meaning? Meaning the effect of axial force and bending moment has to be ignored. Bending moment and shear force, sorry, axial force and shear force and shear force has to be ignored. Okay. Now we are going to see the stress strain behavior of this. Okay. Stress strain diagram for the variation of stress strain diagram for this plastic analysis. See, we are going to see. So there was a rectangular section. Let us take this is the steel bar. Okay. No, this is the entire thing is a steel structure. So let us consider as it is. And this is the centroid or a neutral axis. So this is the neutral axis. Okay. And this is your breadth and this is the depth. This is the depth. Okay. Now Okay, first the strain distribution diagram. Okay, you have to draw the strain distribution diagram. You know, this is the strain distribution diagram. The strain is linear. The strain is linear. Okay, so this is the strain diagram. Okay, this is the compressive strain, for example. This is the tensile strain if it is a simply supported beam. Okay, fine. This is the compressive strain. This is the tensile strain. Now the stress distribution diagram that we are going to draw now. Okay, now the first thing is this is the stress distribution diagram we are going to draw now. Okay, this is the strain diagram. Strain diagram. Now the stress diagram is this. So the stress diagram, this is stress, compressive stress. This is the tensile stress. So this is the yield stress. Sorry, stress. FF. Okay, top is a compression, bottom is a tension. Okay, now this stress is less than the yield stress, and this also less than the yield stress. Okay, while loading, this cross section is subjected to a bending stress. The bending stress top is F and bottom also F, and that value is less than the maximum, that is a yield stress. Okay, now further if you load it, further if you loaded the beam, then you know what happened. If you loaded the thing further, if you loaded this further, if you loaded this further, then then this is, this reaches into the F reaches into the yield stress if you load it further. Okay, and this F reaches into F. If we load it further again, then you know what happened. The yield stress will shift towards the center, that is a neutral axis. So meaning now all fibers are trying to subject to yield stress. Okay, all fibers. Okay, so meaning if you increase the load further, then this one here the yield stress is subjected. Here also the yield stress is subjected, and the center portion maybe it will be something like that. And if you loaded the beam further, if you loaded the beam further, then the entire cross section is becomes as, the entire cross section becomes as yield stress. Okay, so that means in this case we can conclude this is the stress. We can conclude okay, is something like that. You will get a diagram. So the stress diagram you will get something like that. For this case also, your neutral axis gets shift. Okay, like that. Now this section is throw out, this is Fy, and up to here also Fy, then there was a elastic stress. And here also this is Fy, but throughout depth there was a Fy. Okay. Now, this is the moment at a safer zone. This is the moment, this is the stress corresponding to the yield stress. This is the stress for a certain depth of the beam corresponding to the yield stress. This, the entire depth of the beam is subjected to yield stress. Okay. Now, bending moment is equal to, we know that generally F into Z. Here F means what? The stress which is less than yield stress. Okay. Next one is here moment is equal to Fy into Z. Okay. So this is section modulus. This is also section modulus. So now here M is equal to Fy into Z. So this is also a moment. Now, this is equal to moment is a plastic moment. Why? Fully plastified section. Okay. So, into Fy into corresponding Z is equal to Zp. Okay. Now, this moment is called it as safe moment of resistance. Safe moment of safe moment of resistance. That's the first one. And the second one is this a yield moment of resistance. Yield moment of resistance. Why yield moment of resistance? See, here the stress is corresponding to yield stress. That is the reason. Next one is, this is okay. The moment of resistance for a semi-plastic state. Moment of resistance for a semi-plastic state. Okay. What is semi-plastic state? So for this portion, certain depth we are having elastic stress. Okay. So that's why some portion will be plastic. Up to here is a plastic. Below this also plastic. So that's why we are saying this is the moment of resistance for a semi-plastic section. Semi-plastic section. Okay, then MP, it is the plastic moment. MP is the plastic moment. Plastic. MP is the plastic moment. So these are the data. Now, this is the neutral axis. This is the neutral axis. And this point is the equal area axis. The fully plastified section, this neutral axis gets shifted either up or down. So this is the equal area axis. Okay, this is also equal area axis. What is EAA? EAA is equal to equal area axis. Okay, equal area axis. Now what is the shape factor. The shape factor is defined as, we can write, it is defined as the yield moment capacity divided by working moment, plastic moment capacity divided by yield moment capacity. That is, this is the plastic moment, fully plastified. The ratio between these two moments, we can call it as is the shape factor. The ratio between these two is called as shape factor. The ratio between plastic moment and the safe moment, we can call it as a load factor. The ratio between plastic moment divided by the safe moment is called as load factor. Okay, so these are the some of the points that you have to keep in mind. Now we are going to write shape factor. Shape factor is equal to plastic moment to yield moment. Plastic moment to yield moment. Okay, so now we can write this, which is equal to MP divided by M. What is MP? ZP, okay, into Fy divided by what is M? Z into Fy. That is a yield moment. Okay, M is equal to what? M is equal to Fy into Z. What is the fully plasticized section? MP Fy into ZP. Right? So this is ZP divided by Z. That is a safe factor. Therefore, the safe factor is equal to ZP by Z. Okay. Now, next one is a load factor. So load factor is equal to, we can write first of all safe factor. Note shape, not a shape. Shape factor is greater than always greater than 1. Okay, shape factor is always greater than 1. That's the first point you have to keep in your mind. The next one is shape factor is always greater than 1. Now, second one is shape factor represents reserve strength of beam reserve strength of beam section beyond yield moment. The shape factor means it represents the reserve strength of beam section beyond the yield moment to reach the plastic state to reach the plastic state. Okay, more shape factor more shape factor more shape factor implies more reserve strength beyond yield moment to reach plastic state So this is the point, meaning, for example, in a elastic state or a yield state, for example, on a steel, what is the yield stress for a steel? That is 250. This is also 250. Then if you calculate the elastic state moment is equal to Fy into Z. So if you simplify this, then for example, I'm saying for example, this is 300 kilonewton meter. But at the same time, this is the yield stress. Throughout depth, there was a yield stress. But in this case, only top and bottom fiber is subjected to yield stress. Remaining depth is subjected to stress less than the yield stress. That's why we are getting a triangle. Okay. But in the plastic state, throughout the depth is subjected to yield stress. So this is the plastic state. This is Fy. Okay. Now this is MP, which is equal to, for example, so this is Fy into ZP. For example, MP is equal to, let us consider 500. Now what is the shape factor? Shape factor is equal to 500 divided by 300 is equal to 5 divided by 3 is the answer. So it always greater than 1. Okay, so this value is equal to now 1.67. Okay, so this is the answer. Now we are going to see load factor. Shape factor is over. Now is load factor. Load factor, it is defined as, load factor is defined as, load factor is defined as the ratio of ultimate load divided by working load. Divided by working load. Okay, this is for RCC member. Then one more formula, load factor, which is equal to plastic moment capacity, plastic moment capacity divided by safe moment capacity, safe moment capacity, that is in steel. So the load factor we can write plastic moment capacity is Fy into ZP, right? Plastic moment means what? Fy into ZP. Safe moment is what? F, not Fy. Safe moment is F into Z. Now this Fy divided by F, the yield stress divided by F is the permissible stress. Okay, so Fy divided by F is equal to, we can write this a factor of safety. Zp by Z we can write is a safe factor. Therefore, load factor is equal to is the important relations factor safety into safe factor. Okay, okay, and moreover, this formula applicable for applicable for ductile material, not for brittle material. Not for brittle material. Okay, so these are the important points. Okay, so this is all about the load factor. Okay, now we are going to write some of the important points. Footnote. For the fully plastified section, for the fully plastified section, bending moment is bending moment is called plastic moment. For the fully plastified section, bending moment is called plastic moment, that is MP, and and curvature. Okay, and curvature becomes infinity. For a fully plastified section, bending moment is called plastic moment, and for a fully plastified section, the curvature is infinity. Okay, so this is the important point that you have to keep in your mind. Okay, now this is the first point. Second point, plastic moment, plastic moment, MP, is independent of length of length and loading of the beam. Loading of the beam. Okay. Now, third one, shape factor, which is equal to, we have written ZP divided by Z. Here ZP is equal to total area divided by 2 into Z1 plus Z. Sorry, not Z1. Okay. Okay, I think it got deleted. So let me write once again. Put note and write. Okay. For a fully plastified section, bending moment is called plastic moment, and the corresponding curvature is infinity, and the corresponding curvature is infinity. So this is the note number 1 point. Now the second one is note number 2. MP plastic moment is not dependent upon the length of the beam and loading of the beam. It is not depends upon the length and loading of the beam. Okay. Third one is, we know that shape factor, which is equal to ZP by Z. ZP is equal to A divided by 2 into Y1 bar plus Y2 bar. So this Y1 bar and Y2 bar, which was taken from neutral axis. So this is, we are taking from the, sorry, this is not a neutral axis, from equal area axis, from equal area axis. Okay. Now what about Z? Now Z is equal to moment of inertia of that particular section divided by 1. Okay. Now the next point is, we can go for shape factor for different shapes. Shape factor for different shapes. The first one is, okay, I can write, for a rectangular section, for a circular section, a triangular section symmetrical about y-axis, a triangular section symmetrical about x-axis, a diamond section, a H section. So the section is H, and I section, then hollow circular section. It's a very thin. Okay. Then for rectangular section, this value will becomes is around 1.5. This is safe factor is 1.5. This safe point factor is equal to 1.7. This is not symmetrical about y-axis. Therefore, this is 2.34. And this is symmetrical about x-axis. Therefore, this is 2. For diamond section 2, H section is 1.5. I section 1.12 to 1.14. We can go up to that mark. Okay, so this is the safe factor for different section. You have to keep in your mind while going your examination. Okay,